I'm sure you've heard the news. Kafka is saying goodbye to ZooKeeper. Here's what it means for you. For a long time, Apache Kafka has leaned on ZooKeeper for key functions like controller election, cluster membership, topic configurations, access control lists, and quotas. But ZooKeeper has its flaws, scalability issues, added complexity, and consistency challenges. First off, controller election. ZooKeeper helps decide the main controller among the brokers by creating temporary nodes. The first broker to succeed becomes the controller, but this process can slow things down during failovers. Next, cluster membership. ZooKeeper tracks which brokers are in the cluster. If a broker disconnects, its node is deleted. Handy, but it introduces a bottleneck. How about topic configurations? ZooKeeper stores all the details, from the number of partitions to the location of replicas. And it's the same for access control lists, managing who can read or write. But here's the kicker. ZooKeeper struggles with scalability and consistency. As Kafka clusters grow, ZooKeeper can't keep up, affecting performance and availability. Plus, maintaining ZooKeeper is a headache, adding complexity to an already complex system. So what's the solution? Kafka is moving away from ZooKeeper to a new consensus protocol built into Kafka itself. This means faster failovers, better scalability, and less hassle. Stay tuned, because Kafka's evolution is just getting started. Say goodbye to ZooKeeper and hello to a sleeker, more efficient Kafka. To understand why this shift is monumental, let's delve deeper into the intricacies of Kafka and ZooKeeper. Apache Kafka, a distributed event streaming platform, has been a cornerstone for real-time data pipelines and streaming applications. It's known for its high throughput, fault tolerance, and durability. ZooKeeper, on the other hand, is a centralized service for maintaining configuration information, naming, providing distributed synchronization, and providing group services. It's been the backbone for Kafka's metadata management. However, as Kafka deployments scaled, the limitations of ZooKeeper became more pronounced. The complexity of managing a separate ZooKeeper ensemble, ensuring its high availability, and dealing with its performance bottlenecks became a significant overhead. One of the critical pain points has been the controller election process. In a Kafka cluster, the controller is responsible for managing the state of partitions and replicas. ZooKeeper's method of electing a controller by creating ephemeral nodes can be slow, especially during failovers, impacting the overall availability of the Kafka cluster. Moreover, ZooKeeper's handling of cluster membership, where it tracks which brokers are part of the cluster, can introduce delays. If a broker disconnects, ZooKeeper deletes its node, but this process isn't instantaneous, leading to potential inconsistencies. Topic configurations, another critical aspect, are stored in ZooKeeper. This includes details like the number of partitions, replication factors, and the location of replicas. While this centralization is handy, it also means that any issues with ZooKeeper can directly impact Kafka's performance. Access control lists, ACLs, are also managed by ZooKeeper, determining who can read or write to specific topics. This adds another layer of dependency on ZooKeeper, making Kafka's performance and scalability tightly coupled with ZooKeeper's efficiency. The scalability issues with ZooKeeper become more evident as Kafka clusters grow. ZooKeeper's architecture isn't designed to handle the massive scale that modern Kafka deployments demand. This leads to performance bottlenecks and challenges in maintaining consistency across the cluster. Maintaining ZooKeeper is no small feat. It requires careful configuration, monitoring, and tuning to ensure it performs optimally. This adds complexity to the overall system, making it harder for organizations to manage their Kafka deployments efficiently. Recognizing these challenges, the Kafka community has been working on a new consensus protocol, Kafka Raft. This protocol is designed to replace ZooKeeper, integrating directly into Kafka to handle metadata management and controller election. Raft aims to simplify the architecture by eliminating the need for a separate ZooKeeper ensemble. It leverages the Raft consensus algorithm to manage metadata, ensuring faster failovers and better scalability. With Raft, Kafka can handle larger clusters more efficiently, reducing the operational overhead and improving overall performance. This shift is expected to make Kafka more robust and easier to manage, paving the way for even larger and more complex deployments. The transition from ZooKeeper to Raft is a significant milestone in Kafka's evolution. It reflects the community's commitment to continuous improvement and addressing the real-world challenges faced by users. So, as we bid farewell to ZooKeeper, we welcome a new era of Kafka, one that promises greater efficiency, scalability, and simplicity. Stay tuned because the best is yet to come.